Invitation. I would like to thank you and the organizing committee for putting together this exciting and great conference. I hope next time will be in person, so I will have a chance to visit Morocco, which I'm
I
looking
hope so.
for
Yeah,
that.
I hope so.
So today I'm going to talk about the quantum energy teleportation on a quantum computer. And as Ahmed mentioned, this project led by my postdoc Sang Wu and Dr. Manas Sejan, and the funding from the Quantum Science Center. This is a DOE center. So here's the overview. First of all, I will tell you what is quantum state teleportation. A lot of us are familiar with this concept, how to teleport secure information between two different places. And then this will inspire us to go to quantum energy teleportation. Can we talk about energy teleportation? And to talk about energy teleportation, you have to define the concept strong local passive states, which means states that cannot extract energy out of these states. So you need something special to extract energy from these special states. And then I will talk about our new work, how to amplify this teleportation and how one can implement this procedure on a quantum hardware, a quantum computer. So first of all, briefly, just to set the stage, what is quantum state teleportation? And you see the protocol was proposed back in 1993 by Charles Bennett, who was at IBM, and other co-author of this physical review letter from 93. And the main idea, suppose we have two parties, Alice and Bob, and Alice would like to send secure information to Bob, and the information is encoded in this state. And this is we call the qubit. It's a superposition of two bits, 0 and 1. And the alpha and beta are complex number, you have to normalize it. So the way they send secure information, they have to share two entangled qubits. One will be at Alice's side, and the other one will be at Bob. And then Alice will do measurement on her side and use classical communication to tell Bob, said, oh, I did this measurement, and here is the results. And Bob has one of the qubit, which is entangled with her two qubits, and once he receives the information from Alice, then he will do the transformation to recover the secret information that Alice wanted to send it to him. So I thought maybe just show pictorially how this works. So you can see here, Alice has a qubit. This is the information that she would like to send to Bob. They share a pair of qubits in an entangled state, and this is 0011 is a maximum entangled state. Entangled state means they have strong correlation. If I separate them at infinity and I do measurement on one, the outcome of the other one will be decided by the other measurement. So although you separate them, they still talk to each other and affected by the measurement on one side. So you can see we sent two entangled qubits, one to Alice and one to Bob. And now we have three qubits in the system. The blue one is the one we'd like to teleport to Bob, and the red are the entangled pairs. So you have the wave function for the three particles, and you see it's a sum of four terms. On the left-hand side of this sum, you have maximal entangled state. These are the four Bell states, and these are maximum states. And you can see there is also information on the right-hand side. So the protocol works like this. Alice will do measurement. And let's say she got measurement on the Bell state. She got the 0, 1, which means the second one on this left-hand side. She will have the phone, call Bob and said, oh, I got 0, 1. And Bob knows exactly what to do. He will do the Z transformation to recover the qubit that she is sending. So this was alpha 0 minus, but he will do transformation. He knows what the transformation, and he's the only one can change it because this is his qubit. And if she gets 0, 0, he knows what to do. Nothing is the identity is 1, 0 or 0, 1. So you have 2 bits. So you have 2 classical bits and 2 entangled qubit, which allow you to transfer information between any 2 distances. And we can also do this on a quantum circuit. Here, for example, the 3 qubit quantum circuit, each line is a qubit, each box is a quantum gate, and Alice has the information, the secure information that you would like to send, alpha 0 plus beta 1, and after you do this operation, you end up with Bob receiving the information. So people start, this is a new concept, so they start doing teleportation on a small scale in the lab. And I remember this was our paper from 2006, almost 20 years ago. People were doing teleportation using quantum dots. And you can see the progress. Then you have 600 meters. People went up to teleportation 16 kilometers. And you can see the progress with time. So it took the community maybe 20, 25 years to scale up this from nano scale into kilometers of teleportation. And if you look today on the people doing satellite-based teleportation, this is the famous Chinese experiment from 2017. They were able to transform using photonic as a qubit to teleport information from the Earth to satellite with thousands of kilometers. And if you look at fiber optic space communication, people now do it with hundreds of kilometers, sending secure information between 2 places. So we went from a theoretical proposal or protocol to technology, and there are many companies using these techniques to send secure information between 2 places. And all of us, we remember from last year, the Nobel Prize in Physics went to the people did the early experiment showing entanglement is a true phenomenon in quantum mechanics. And Anthony Zellinger, he was the one, he pushed it into teleportation for large distances. So now I would like just to shift to quantum energy teleportation. And here we have a different concept. It's not information, we have energy. So what we require from this, we require that, again, I would like energy from A to B, but we are not transferring energy. So you see in a minute how the concept works. So we have a ground state. It's an entangled state between the 2 parties. Alice is going to do measurement on her side. And if she does measurement on her side, nothing happens. Bob cannot extract energy. So what we have to do, once she do the measurement on her side, she's going to communicate classically with Bob and let him know what kind of measurement she did. And once Bob receives the classical information from her, he will be able to extract energy which was not available to him before. And this is the new concept. It's like you can think about it, this is the vacuum state. And you say the vacuum is a 0 energy, nothing happens. It's not, it's full of physics. You have fluctuations in the background, in the 0-point energy and in the vacuum. And this protocol, I mean, I will show how this works, but this is the protocol. You come up with a ground state with entanglement. It's a passive. Nobody can extract energy because this is the ground state. Alice is going to do measurement, which means you could excite the system. At this point, Bob cannot extract energy from his side. She has to tell him the output, and Bob will extract energy which was not available to anybody before. So this is the protocol. And this protocol was proposed back in 2008 by Masahiro Ohata. He's a theoretical physicist at Tokyo University. And just me show you pictorially how this works. You have Alice and Bob, and we are looking at the energy density as a function of their location. Alice, she's going to do measurement on her side. By doing measurement, you inject energy into the system. For example, you excite the system or you do whatever in this side with Alice. And suppose she did inject energy into the system and the output was in here. And then you can think about it, this way, the energy density will move. So Bob cannot extract any energy from his side until he received the output of the measurement. And then he said, oh, once I have the output of measurement, I know what is the transformation I need to know to extract energy from negative energy density. So here's the concept. There is locally negative energy density, which nobody can extract until he know what is going on the other side. And this is the protocol that he put together back in 2008. And then it took the community a long time to show this in an experiment. And physical review letter back in 2023, the group at the University of Waterloo, the Institute for Quantum, the Institute for Quantum Computing, they use NMR to transfer energy. This is the system, the NMR system. So the 3 carbon atoms, C1, C2, C3. So Alice sitting in C1, Bob in C3, and they use one in the middle called ancilla here. And they were able to show experimentally, if Alice do measurement on carbon atom 1, Bob can extract energy by knowing what Alex did the measurement. And they show beautiful experiment with NMR. They publish it in Physical Review Letter. And the same year, there also was an experimental verification of this teleportation of energy using superconducting quantum hardware by ICOSES here. So let me just, and again, just to complete the story here before we go into the details, you can see here when people listed the biggest breakthroughs in physics in 2023, all of us will remember the gravitational wave and other phenomena, but quantum energy teleportation was one of the biggest breakthrough in 2023, since you have the protocol, the theory side, and the experiment with NMR, and the experiment with superconducting qubits. And this was 2008 by Hota. So let me just go through the procedure and then a little bit detail so you can see how we extract energy. So Alice is going to inject energy in the system, but still the whole system with Bob where he's going to extract energy, I will explain this concept called strong local passive states, which mean nobody can extract energy out of these states. So you can think about it, the vacuum state or the 0-point energy state, the ground entangled state. So what he needs the key to extract energy. And this key he will be getting from Alice. And again, so he will get the key, which means what is the outcome of the injected energy in the Alice side. He will take this key, and then there is a negative density energy in his side, and this is locally. And he will extract this energy where was not available to anybody before. Nobody knew about this energy except if he got the key for that one. So you can see what are the essential elements. We need ground state to connect A and B. We have entanglement and local measurement. Alice is going to do local measurement on her side, and Bob is going to extract energy. So there is no teleportation. Energy is not moving from Alice to Bob. She has to inject energy and then tell Bob about it so he can extract energy from his side. So let me go to the model to see how it works in a model system, and then show you how one can implement this in a quantum computer. So again, we have two parties, and you can think about two-level system at A, two-level system at B. And here is the Hamiltonian. You have two-level system, and these are Z and X are Pauli operators. So the Z is a two-level system, plus and minus one on Alice. Bob has the same two-level system, and there's interaction between them, connecting the two, A and B. And the interaction with the Pauli X. So again, if Z is pointing up or down, X is pointing in the X direction, plus or minus. So these are the Pauli spin matrices. And the ground state for this system is entanglement. 0, 0 plus 1, 1 is an entangled state, meaning I cannot factorize it into two individual states. And if I do measurement on the first one, 0, I know the second one is 0 if I separated them at infinity. So now let's look at the protocol. Alice is going to do measurement, and the way she's going to do the measurement, we call it, they do measurement in the Hadamard base or in the plus minus state, or they call it also Fourier bases. And plus and minus is a combination, 0 plus minus 1. And by do measurement, she inject energy, like exciting the spin from ground to excited state. She inject energy in this state. And then from her side, she got energy out of this injection or the projection on their side. But at this point, Bob doesn't know about all of this and he cannot extract energy. So Bob still cannot extract energy. She has to tell him what is the outcome of her projection. If the projection was a plus, she will tell him, I got plus. He know what to do, the rotation in his side to extract energy. If the outcome was minus, she will tell him, I got minus. He will do the rotation in his side and extract the energy. So essentially, this is the protocol. Bob will extract energy by knowing the outcome of the measurement on the other side. And again, remember, this protocol is already verified experimentally with NMR and superconducting qubits. So now I would like to just explain the concept strong local passive state, because this is state that nobody can extract anything out of it. And again, think about the vacuum state or 0-point energy state or ground state, that you cannot extract any energy out of this. So just to define passive state, so you see, you can distinguish between passive state, local passive, or strong local passive. So passive state, like in thermodynamics, if you have a cyclic process, you start from one end and go back to that end, you cannot extract energy. And you can see this mathematically, that the trace U is the operator. If you take rho U dagger U, you get rho, this is the density of state as a function of time. So if you do cyclic motion, that you cannot extract energy, the energy will be positive here. Locally, if you apply the unitary operator locally, for example, Alice is doing measurement and Bob is going to extract locally energy, but not on the whole space. So it's called local passive state. And the third one, if it's strong local passive, which means any operation on your side cannot allow you to extract energy. And there is a mathematical formalism. I will not go to the detail. There is a theorem. How do you check if the state for given density of state and a Hamiltonian, if it's strongly passive or local passive? There is a mathematical theorem where one can calculate this matrix and look at the eigenvalue. So again, all these details in our paper, if one would like to see the appendices, how this works, but mathematically we know how to decide if a state is strongly passive or not. Can you extract energy out of it or not? So we have to make sure the state that we're starting the protocol cannot be extract energy out of it locally or globally. So just to summarize what we have in this protocol, we need a ground state. We need one side, Alice, to do the measurement, communicate the results with Bob. Bob will do operation on his side locally and extract energy. And we need to have entanglement between the two sides. So once she do the measurement, the other side will be affected. So what we have done recently, we saw, okay, is there any way we can really relax these constraints and make it more general? Not only to look at the ground state, can we look at other states in the system and expand the scope of application of this phenomena? And yes, we succeed to do that. And the idea is, instead of starting with just XX interaction between Alice and Bob, try to generalize it, what we call XY interaction. Again, X, Y, and Z these are Pauli operators. And you can see here, we modify the interaction between them. So if you modify the Hamiltonian or the interaction between you two parties, this will allow you to expand the scope of this phenomena. And this is what we have done in this paper. So if one looked at the energy of this state, you have 4 states. So look at the ground state is entangled state, but we said, okay, can we go to the second excited state, 0, 0? It's a factorizable, it's 0 times 0. So when we looked at this state, it turns out that this state is SLB, which means nobody can extract energy out of it. So this was the first part. You don't need an entangled state. You could have also an excited state, but with the condition that it's SLB, which means you cannot extract energy locally or globally from the state. So again, no entanglement, but then nevertheless, E1, which is the first excited state, is itself SLB, the strong local passive state. So again, when we did this this protocol, and again, we got back to the same thing. Alice will do the measurement in the plus or minus state. Get out the output of this quantum one could be plus or minus. We'll tell Bob, and Bob will do the right rotation. And it turns out you can increase the energy extracted by Bob by modifying the interaction between them by almost 7 times. So we went from 0.01 to 0.08. So this allows us to expand the energy extracted by this protocol by modifying the interaction between the two parties. And just to summarize, now we don't need a ground state because E1 was excited state. And the commutativity, how the projection operator commute with each term can be relaxed. And here 0, 0 is not entangled. It's a factorizable 0 times 0. So somehow this allows us to really expand the scope of this phenomena and show one can also extract energy out of this, what we call strong local passive states with different interactions. And here we can explain this phenomena more pictorially, what happens. You can ask the question, if there is no entanglement, how did Bob, by receiving information from Alice, knew what to do? So we went through all this mathematics and geometrical picture to explain how this works. And the conclusion out of this, it turns out it depends how do you rotate the states. So I'm not going into the details, but we have also a mathematical and geometrical picture to explain why Bob receiving information from Alice can do the right thing and extract energy. And just to summarize, they start from 0 and the departure was different outcome. If a plus, you go to plus states, and this is go to G plus. And if the outcome minus, you go to another state. So although they start from 0, the outcome, this destination is different if the outcome was a plus or minus, which means Bob can decide what to do after he received the information from Alice. And we explain, without going to the mathematical details, that why the energy was around 7 times larger in this protocol than in the old protocol. And now we said, okay, can we also run it on a quantum computer? And the answer is yes. We can run this protocol, and we have here the qubits, Alice qubit, and Bob here the qubit. Remember, solid line is a qubit, and 2 closed line is the classical communication, classical bits, so 0 or 1, but the solid line in the quantum circuit means qubit. And each box is a quantum gate. Like this is the Hadamard. Hadamard will take 0 into 0 plus 1 and take 1 into 0 minus 1. So all these are the quantum gates needed to perform the measurement. And then you have the conditional operation. So you can see the 2 lines are the classical bits. They will tell Bob if the outcome was plus or minus, and if it's plus, he will rotate with the minus sign. And if it's minus, he will rotate with the plus sign and do measurement on a quantum computer. And my postdoc, Song-Woo, did this calculation on the IBM quantum computer and calculate the averages. And you can do the same thing analytically. And he got almost the same results from both measurements. From the analytical results, here are the expectation value and the quantum computer. And you can see analytical was 0.80. 0.802. The simulation and IBM, he used different IBM quantum computer, and you can see the results within the error 0.82 plus minus. So anyway, we confirm this, the new protocol, by applying this on the IBM quantum computer. So just to go to the summary and conclusion, in this protocol, we need what we call the SLB, the strong local passive, which means a vacuum or 0-point energy or state that you cannot extract energy. But if you disturb the system at a distance and give the information to the other side will know for sure what to do in order to extract energy. And we start with the simple protocol, and then we generalize it. So you can see what is the future for this kind of protocol. Can we apply it on nano devices? I mean, this is exactly, I mean, if you look at the history of quantum state teleportation, we start with the quantum dots and the small scale, and now we have thousands and hundreds of kilometers of transferring secure information. And now with the energy, it's a little bit more delicate because, I mean, how do you connect the two sides? It's still scaling of these devices. It's a future work. So can we also induce reaction at the other end? When you extract energy, can you induce another reaction? What are the physics of these devices? And can we scale it up? I would like to end by thanking my research group, because we're trying to take it in a different direction, and the funding agencies. And I would like to thank you for your attention. And if you have any questions or you have anything to communicate after this talk, I mean, you have my email, and I will be happy to answer any questions. Thank you.